Basic computer organization. Learning objectives. In this chapter, the user would learn the following in detail: instruction codes, direct and indirect address, timing and control signal generation, instruction cycle, memory reference instructions, input-output instructions. Introduction. Every processor type has its own design, different registers, buses, micro-operations, machine instructions, etc. Modern processor is a very complex device. It contains many registers, multiple arithmetic units for both integer and floating point calculations, the ability to pipeline several consecutive instructions to speed execution, etc. The basic computer. The basic computer has two components, a processor and memory. The memory has 4096 words in it. 4096 equals 212, so it takes 12 bits to select a word in memory. Each word is 16 bits long. Instruction codes. Program, a sequence of machine instructions. Machine instruction code, a group of bits that tell the computer to perform a specific operation, a sequence of micro-operation. The instructions of a program, along with any needed data, are stored in memory. The CPU reads the next instruction from memory. It is placed in an instruction register. Control circuitry in control unit then translates the instruction into the sequence of micro-operations necessary to implement it. Medium to large-scale computing systems may have hundreds of instructions. Most small computers limit the list to less than 100 instructions. Operation code. A group of bits that define such operations as add, subtract, multiply, shift, and complement. A number of bits required for the operation code of an instruction depend on the total number of operations available in the computer. A portion of a machine language instruction that specifies the operation to be performed. Example: load, store, add, jump. A computer can perform operations, each of which is assigned a numeric code called an opcode. Opcodes operate on registers, values in memory, values stored on the stack, input-output ports, the bus, etc. Stored program organization. A computer is to have one processor register and an instruction code format with two parts. The first part specifies the operation to be performed, an opcode, operation code, that specifies the operation for that instruction. The second part specifies an address. An address that specifies the registers and/or locations in memory to use for that operation. The memory address tells the control where to find an operand in memory. Instructions are stored in one section of memory and data in another. Memory codes. Stored program organization. For a memory unit of 4096 words, we need 12 bits to specify an address, since 212 equals 4096. If we store each instruction code in one 16-bit memory word, we have available 4 bits for the operation code, abbreviated opcode, to specify 1 out of 16 possible operations, and 12 bits to specify the address of the operand. The control reads a 16-bit instruction from the program portion of memory. It then executes the operation specified by the operation code. Computers that have a single processor register usually assign to it the name accumulator and label it AC. Any operation that does not need a memory operand frees the other bits to be used for other purposes, such as specifying different operations. Direct and indirect address. The address field of an instruction can represent either direct address, the address in memory of the data to use the address of the operand. The operand's address is stored within the instruction word. The operand is at the location specified by the address stored within the instruction word. Example: add A. Add contents of cell A to accumulator. Look in memory at address A for operand. Single memory reference to access data. No additional calculations to work effective address. Limited address space. Indirect address. The address in memory of the data to use. The operand's address is stored within another memory register whose address is specified within the instruction word. Memory cell pointed to by address field contains the address of pointer to the operand. Example: add A. Add contents of cell pointed to by contents of A to accumulator. Large address space. Effective address EA. The address that can be directly used without modification to access an operand for a computation type instruction or as the target address for a branch type instruction. Timing and control. The timings for all the registers is controlled by a master clock generator. Its pulses are applied to all flip-flops and registers, including in the control unit. The control signals are generated in the control unit. Provides control inputs for the bus's multiplexers and for the processor registers, and provides micro operations for the accumulator. Control unit CU of a processor translates from machine instructions to the control signals for the micro operations that implement them. Types of control unit. There are two types of control. Hardwired control. Control unit is made up of sequential and combinational circuits to generate the control signals. Microprogrammed control. A control memory on the processor contains microprograms that activate the necessary control signals. Hardwired control unit. It is implemented as logic circuits, gates, flip-flops, decoders, etc. in the hardware. This organization is very complicated if we have a large control unit. In this organization, if the design has to be modified or changed, requires changes in the wiring among the various components. Thus, the modification of all the combinational circuits may be very difficult. Hardwired control unit architecture shows the architecture of hardwired control unit. Hardwired control unit. Advantages. Hardwired control unit is fast because control signals are generated by combinational circuits. The delay in generation of control signals depends upon the number of gates. Disadvantages. More is the control signals required by CPU, more complex will be the design of control unit. Modifications in control signal are very difficult. That means it requires rearranging of wires in the hardware circuit. It is difficult to correct mistakes in original design or adding new feature in existing design of control unit. Microprogrammed control. A microprogrammed control unit is implemented using programming approach. A sequence of micro operations is carried out by executing a program consisting of micro instructions. Microprogram consisting of micro instructions is stored in the control memory of the control unit. Execution of a micro instruction is responsible for generation of a set of control signals. Microprogrammed control architecture shows the architecture of microprogrammed control architecture. Microprogrammed control. Advantages. The design of microprogram control unit is less complex because microprograms are implemented using software routines. The microprogram control unit is more flexible because design modifications, corrections, and enhancement is easily possible. The new or modified instruction set of CPU can be easily implemented by simply rewriting or modifying the contents of control memory. The fault can be easily diagnosed in the microprogram control unit using diagnostic tools by maintaining the contents of flags, registers, and counters. Disadvantages: the microprogram control unit is slower than hardwired control unit. That means to execute an instruction in microprogram control unit requires more time. The microprogram control unit is more expensive than hardwired control unit in case of limited hardware resources. The design duration of microprogram control unit is more than hardwired control unit for smaller CPU. Timing and control signal generation. All the operations in the computer are synchronized by the master clock generator, whose clock pulses are applied to all flip-flops in the system. In addition, a certain number of timing variables are available in the control unit to sequence the operation in the proper order. These timing variables are designated T0, T1, T2, and so on. The clock pulses occur once every microsecond, µs. Each timing variable is 1 µs long and occurs once every. Control unit of basic computer. Control unit consists of two decoders, a sequence counter, and a number of control logic gates. An instruction read from memory is placed in the instruction register IR. The instruction register is divided into three parts: the 1-bit, the operation code, and bits 0 through 11. The operation code in bits 12 through 14 are decoded with a 3x8 decoder. The 8 outputs of the decoder are designated by the symbols D0 through D7. The subscripted decimal number is equivalent to the binary value of the corresponding operation code. The 4-bit sequence counter can count in binary form from 0 through 15. The outputs of the counter are decoded into 16 timing signals T0 through T15. The sequence counter SC can be incremented or cleared synchronously. Timing signals generated by 4-bit sequence counter and 4x16 decoder. The SC can be incremented or cleared. Example: T0, T1, T2, T3, T4, T0, T1, and so on. Assume at time T4, SC is cleared to 0 if decoder output D3 is active. Instruction cycle. A process called the instruction cycle carries out the instruction of a program. The instruction cycle consists of three phases. Fetch an instruction from memory. Decode the instruction. Read the effective address from memory if the instruction has an indirect address. Execute the instruction. After an fetch and decode. An instruction is read from memory during the fetch cycle. The instruction cycle consists of the fetch cycle and the execute cycle. The fetch cycle is identical for all instructions. The execute cycle is different for different instructions. The address of the next instruction is stored in PC. A memory data register MDR resides in the CPU, which holds data items for communication. The address information to the memory is held in the memory address register. Fetching. Transfer of the address from the program counter PC to memory address register MAR. Generation of the read control signal. Waiting for the memory to transfer the instruction or data into memory data register. The instruction code is then stored temporarily in instruction register for decoding. After the instruction is decoded, the content of the program counter will be updated and the fetch cycle completes. The execute cycle. The CPU performs the different tasks according to the instruction. Different resources will be required for different types of instructions. At the end of the execute cycle, the contents of the processor status register will be updated. Register reference instructions. The 12 register reference instructions for the computer are listed in the following table. Each register reference instruction has an operation code 0110 hexadecimal 6 and contains a single 1 in one of the remaining 12 bits of the instruction. These instructions are specified with 4 hexadecimal digits which represent all 16 digits of an instruction word. The first 7 instructions perform an operation on the A or E registers. The next 4 are skip instructions used for program control conditioned on certain status bits. To skip the next instruction, the PC is incremented by 1 once again. The first increment occurs when the present instruction is read. The halt instruction is usually placed at the end of a program if one wishes to stop the computer. Memory reference instructions. The 6 memory reference instruction for the computer is shown. The 6 memory reference instruction for the computer is: the symbolic designation is a 3-letter word and represents an abbreviation. The hexadecimal code listed is an equivalent hexadecimal number of the binary code adopted for the operation code. A memory reference instruction uses 1 hexadecimal digit, 4 bits, for the operation code. Remaining 3 hexadecimal digits, 12 bits, of the instruction represent an address. AND to A. This is a logic operation that performs the AND operation on corresponding pairs of bits in A, with the memory word M specified by the address part of the instruction. The result of the operation is left in register A, replacing its previous contents. Add to A. This instruction adds the contents of the memory word M specified by the address part of the instruction to the present contents of register A. If addition done for negative numbers are in their 2's complement form, the end carryout of the sign bit position is transferred to the E flip-flop. Multiplication is achieved by adding and shifting. The add instruction must be used for loading a word from memory into the A register. This is done by first clearing the A register with the register reference instruction CLA. Store in A. This instruction stores the contents of the A register into the memory word specified by the instruction address. Increment and skip if 0. ISZ. The increment and skip instruction is useful for address modification and for counting the number of times a program loop is executed. A negative number previously stored in memory at address M is read by the ISZ instruction. This number is incremented by 1 and stored back into memory. If, after it is incremented, the number reaches 0, the next instruction is skip. Branch unconditionally, BUN. This instruction transfers control unconditionally to the instruction at the location specified by the address part M. This instruction tells the computer to take the address part M and transfer it into PC, program counter. Branch to subroutine, BSB. This instruction is useful for branching to a subroutine portion of the program. When executed, the instruction stores the address of the next instruction in sequence, which is presently held in PC, called the return address, into the memory word specified by the address part of the instruction. It also stores the operation code of BUN in the same memory location. Input-output instructions. The computer has 4 input-output instructions and they are listed in the table. These instructions have an operation code 0111, hexadecimal 7. Each contains a 1 in only one of the remaining 12 bits of the instruction word. The input-output instructions are specified with 4 hexagonal digits starting with 7. The INP instruction transfers the input character from N to A and also clears the input flat in N9. The OUT instruction transfers an 8-bit character code from A into the output register and also clears the output flat in U9. The 2 skip instructions check the corresponding status flags and cause a skip of the next instructions if the flat bit is 1. Conclusion. In this chapter, we have covered the following aspects of basic computer organization: instruction codes, direct and indirect address, timing and control signal generation, instruction cycle, memory reference instructions, input-output instructions.